Welcome. So we're going to be solving logarithmic equations in this series of lessons. Right? And so first we're just going to review very quickly through properties of logarithms. Right? This was also I went over this in more detail in solving exponential equations. Right? So we have our product rule, our quotient rule, and our power rule. Right? The reason it has for any real numbers x greater than 0 and y greater than 0 is you can only take logs of positive numbers. And that's because when you raise something to a power, raise a base to a power, you're going to get a positive number. So raise a positive number to a power, you get a positive number. All right, so we have our product rule. Right? If we have log in any base of a product, that's equal to the sum of the logs. Quotient rule. Right? So the quotient, if we have the log of a quotient, that's equal to the difference of logs. And then power rule. Right? So remember, a log is an exponent. And of course, there we have another exponent. And what do we do when we raise power to a power? We multiply exponents. Right? So we can take an x, if we have the log of something raised to a power, that's going to be the same as the product of that exponent as a coefficient times whatever the log equals. Right? So all of these properties are based on the fact that logs are exponents. When we multiply some bases raised to a power, we add the exponents. That's why we have our product rule. When we divide like bases raised to a power, we subtract the exponents. That's why we have our quotient rule. And when we raise power to a power, we multiply exponents, and that's why we have our power rule. Also, in this series of lessons, we're going to be having to rewrite equations from logarithmic form to exponential form. All right, so just remember that there's our base on the exponential. Here's our base on the log. This is the exponent on the exponential. Our log equals the exponent for the log equations. And then you raise something to a power, you get a result. You take a log of that result, and you get the exponent. All right? So we'll be using that to we'll be using exponential, rewriting into exponential form to be able to solve log equations. But in the first series of lessons, we're going to be solving logarithmic equations where we have log equals a log. Right? So we have, at the very, very beginning of all the solving exponential and log equations, I went over all the different types of equations we'd solve in all of these lessons. And one of those was when we have log in some base equals a log in the same base. Right? So solving a logarithmic equation where we have log equals log. And I have to say these are the easiest of the logarithmic equations to solve. Not actually that solving logarithmic equations is all that difficult, but this one's the easiest. So the only way that log in some base of some number is going to be equal to log in the same base of a different number, that's only going to be true if and only if what follows is equal. So the only way that the logs of two different values is going to be true is if those values are the exact same thing. Right? So very important, the bases must be the same. In this lesson, however, we'll only be working with bases that are the same. Right? So here we have natural log of 2x plus 3 equals the natural log of 5x minus 6. The only way that the natural log of 2x plus 3 could equal the natural log of 5x minus 6 is if 2x plus 3 equals 5x minus 6. Right? So if you have the same base logs are only equal when the terms following them are also equal. So you can drop the logs. Right? So here, natural log of 2x plus 3 equals natural log of 5x minus 6 implies that 2x plus 3 has to equal 5x minus 6. Right? That's the only way that can be true. Right? So these are really easy to solve. You just set what follows your log equal to one another and solve for your variable. So if we have 2x plus 3 equals 5x minus 6, right, we can subtract 2x from both sides. Now we've got 3 equals 3x minus 6, and I'll actually just write in there. So just in case anyone had any questions of how we got to 3x minus 6. All right, so now we'll just add 6 to both sides to get variables on one side, constants on the other. All right, so we combine the like variables, we combine the constants, you just add 6 to both sides. So now we have 9 equals 3x, and that's a nice easy equation to solve. You just divide both sides by 3, so x is equal to 3. Now, very important, we can get false solutions on these problems, so we have to check our solutions, right? So for all the log equations, we will check. It's one of our second group of equations where we have to check. We had to check on the radical, we have to check on log. All right, so natural log of 2x plus 3 equals natural log of 5x minus 6. Our answer was 3, and we have to check. Make sure we get a real number. Right? If you get an error message, well, then that's not a solution. All right, so we have natural log of 2 times 3 plus 3 equals natural log of 5 times 3 minus 6. 2 times 3 is 6. 6 plus 3 is 9. So we have natural log of 9. That is a real number. Right? It'll be a decimal. It'll be a decimal. Essentially what it is it's the exponent you'd have to raise e2 to get 9, right? But it will be a decimal. But it is a real number, and it's the exact same answer as we get on the other side, because 15 minus 6 is also 9. Right? So that is a real number. Right? We have a log of the same thing, and it's positive. So no problems here. That checks out just fine. Right? So the check is really easy. It doesn't matter what natural log of 9 is equal to as a decimal. Leave your exact answer there. It's a real number. It's the same thing on both sides. It works out perfect. All right, so let's solve another one. So you can see these ones aren't too difficult. I'm going to solve actually a couple on this tape, and then the rest of them are on the next tape that follows. But neither tape is going to be very long. All right, here's another example. We have natural log of 2x plus 7 equals natural log of x minus 4. Let's see what happens when we solve this one. All right, so we have natural log of blop equals natural log of blop. Just set those two blops equal to one another. All right, so the only way that natural log of 2x plus 7 equals natural log of x minus 4 is if 2x plus 7 happens to equal x minus 4. Right? So log b of x equals log b of y implies that x equals y. So now let's solve for x. All right? So we're going to subtract x from both sides. All right, so we got x plus 7 equals negative 4. We'll subtract 7 from both sides. So we have x equals negative 11. Now let's check this solution. So we always got to check and make sure it works out. So we have natural log of 2 times negative 11 plus 7 equals natural log of negative 11 minus 4. And we simplify both sides, and we get natural log of negative 15 equals natural log of negative 15. And you might think, hey, it checks out. But then if you think for a moment, all right, the sides are equivalent, but wait a minute. Can we raise e to any power and have it become a negative number? No positive base raised to a power will ever become negative. This has no solution. And if you were to plug this into your calculator, you would get an error message, some kind of error message. And actually, I think I can show that to you if I can manage to find the calculator. There we go. Now, the one on the computer is not the friendliest calculator to work with, but it can handle this. So, there we go. All right, so we want 15, and we want that to be negative. All right, and this one's a backwards calculator. I have to type the number and then hit log. And so this is natural log, and we get not a number. All right, so the calculator knows as well that you can't raise e to any number and have it be negative 15. E to any number is positive. Right? Raise it to a negative number, it gets smaller, but it never gets negative. Raise it to a number greater than 1, it's going to keep getting larger, but it never ever becomes negative. All right, so that's why you always got to check your solutions. All right, just because it works just because we get an answer for 2x plus 7 equals, whatever that was, 2x plus 7 equals x minus 4, doesn't mean necessarily that answer is a good one, right? It doesn't work in the log equation. I think we've got one more. All right, so we have log base 2 of 2x minus 1 equals log base 2 of x plus 5. All right, only going to be true if 2x minus 1 equals x plus 5. All right, so we can drop the logs and just set what follows equal to one another. 2x minus 1 equals x plus 5. We'll subtract x from both sides. It's going to give us x minus 1 equals 5. Add 1 to both sides, x is 6. All right, so anytime we have log some base of some value equals log, oops, I don't know why there's a b in there. It should be the same base. If that's in your notes, by the way, just fix it. We're only dealing with the same base. So for log base a of x equals log base a of y, you must check your solutions because we can get false extraneous solutions, and we saw that on the last problem. Extraneous solutions just means you did everything right, but the answer you got does not satisfy the equation. So let's check out 6 here. Log base 2 of 2 times 6 minus 1 equals log base 2 of 6 plus 5. And now we get log base 2 of 11 equals log base 2 of 11. And that checks out. Right? We can plug in log base 2 of 11. That's a real number. And actually, I can show it to you on the calculator. I will have to use the change of base formula. Where's my calculator? There we go. But you will get a real number. All right, I probably should have written it down. So if I want to plug this into the calculator using the change of base formula, I'll write it down first, and then I'll put it into the calculator. Woo. All right, so that value is going to be equal to, and I can use base 10 or natural log. It doesn't make a difference, but it'll be log 11 divided by log 2, or if I like natural log better, I could use natural log 11 divided by natural log 2, and that'll give me a decimal equivalent. Log base 2 of 11 is the exact answer because this is going to be a never terminating decimal. However, you can see that you would get a real number. I guess I'll just use natural. I'll use log base 10. It's right in front of me. All right, so I have to hit 10. They put the base 10 there. But log without any base at all is understood to be 10. All right, so log of 11 gives me 1.04. Right, but we want base 2. Right, so I'm going to divide that, and I have to hit the parentheses, and because I have to hit the 2 first. 2 base 10, log base 10, close my parentheses, equals. Right, so you can see that's a real number, 3.459. Right, that makes sense, right, because 2 cubed would be 8, and 2 to the 4th would be 16. So it's got to be a number between 3 and 4, and that certainly is a number between 3 and 4. I'll actually write that down, 3.459. Just so that you can see that that really is a real number. However, if we take a log of a negative, that is not a real number. Right, so anytime you've got log in one base equals log in the same base, all you have to do is drop the logs, set what follows equal to one another, solve for your variable, but don't forget to check and make sure you get a real number. All right, so the next problem is going to be on the next video, so stay tuned for the next video. Bye for now.